Welcome to all of our listeners. My name is Abby Bauer. I'm an editor for Hordes Dairyman magazine, and I'd like to welcome you to our Hordes Dairyman monthly webinar series. I will serve as the host for today's program, which will focus on heat stress. Yes, it is still early spring, and parts of the country just had a snowstorm last week, but warm weather is just around the corner. And for our listeners that are farther south or in various parts of the world, heat stress could already be making an impact on their dairy cattle. Heat stress has acute effects in lactating cattle, but there are even more profound effects in cows that are in late gestation during the dry period. A wealth of evidence has been accumulated to show that the developing fetus is negatively impacted by heat stress of the dam as well. In this presentation, we'll cover the impacts of heat stress that last long after the initial thermal insult. If you're listening to the presentation live, you have access to a PDF copy of the slides that you can print. You'll find that in the handout section of the GoToWebinar control panel. Also, if you have any questions for our speaker, please type those into the questions section of the control panel, and we'll answer those following the presentation. Today, it is my pleasure to welcome Dr. Geoffrey Dahl as our webinar presenter. Dr. Dahl is the Harriet B. Weeks Professor in the Department of Animal Sciences at the University of Florida. He's also the director of the university's USAID Livestock Systems Innovation Laboratory in Gainesville. Jeff conducts applied and basic research that has a direct impact on dairy production, with a recent emphasis on the effects of heat stress on cows in late gestation and their calves. He served as president of the American Dairy Science Association in 2019 and 2020, and is an elected fellow in the American Association for the Advancement of Science and the American Society of Animal Science and ADSA. Dr. Dahl, welcome to the webinar, and I look forward to hearing your presentation, which is titled The Long-Term Consequences of Heat Stress in Dairy Cattle.
Thanks a lot, Abby, and thanks everyone for jumping online and listening to the presentation. So we're going to move right into it. So as Abby said, we're going to be talking about some long-term consequences of heat stress. Most of the talk will focus on the calf and early life events and some of the things that influence her productivity. We'll also at the end talk a bit about some potential impacts of season of birth, which obviously is going to be related to heat stress, on longevity, as that is an area of growing interest, I think, in the industry and also in our research program. But first, I want to just provide a couple of updates on the impacts in the cow. So all our studies, for the most part, have focused on heat stress during the dry period and the impacts in the next lactation. And these are data from one of our first studies showing the effects. The symbols there in the open circles are cows that experienced heat stress during late gestation, so during their entire dry period. And the animals that are represented by the symbols that are black squares, those are their herd mates that were cooled during that same time period. So just to sort of set up the model that we use, animals are going to be dried off typically around 48 to 50 days before they are due to calve, and then they will immediately move from cooling conditions, because all of our lactating cows are cooled, into a barn where those animals are going to be experiencing shade and good stalls, but we turn off the fans and the soakers. So they don't have any access to cooling during that late gestation phase or the dry period for the entire time, from when they're dried off until the time that they calve in again, and then they go back into cooling. So that's really the treatment that we impose on these animals. It's not as severe as you might expect, because they are under shade, and it's probably going to be similar to the type of conditions that animals would experience during the summer if they're housed outside throughout much of the Northeast and Midwest and even the Pacific Northwest in the US. So the heat stress that we experience here is obviously high temperature and high humidity, but we can experience that in a lot of different places around the US and internationally. So this is just an illustration of the lower milk production that we can expect if animals are exposed to heat stress during late gestation. And it was not just one study where we saw this. This has been shown in numerous studies, just to remind folks if you've seen some of these data before. In every case, every publication that's out there shows that animals that experience heat stress during late gestation are going to produce less milk in their next lactation relative to their herd mates that are adequately cooled. Now, this is not just our lab that has shown this. Other labs as well in Israel and Mexico and Iran, other areas where we would experience heat stress, all show the same sorts of responses. The cows that are cooled make more milk in the next lactation versus those animals that are heat stressed. So these are data that you may be familiar with, you may have seen previously, and just what I wanted to do is kind of set the stage for how we got into looking at this, not only in the cow in the next lactation, but in the calf, and also to update you on a couple of our more recent studies that address some specific questions about late gestation cooling. When we would present these data, we'd get questions about how long we need to cool cows. Can we just cool cows during the close-up phase of the dry period, or do we need to do it for the entire dry period? What about heifers that don't experience a dry period, that are just coming into their first lactation? Is there any advantage to cooling those animals off prepartum in terms of their productivity in that first lactation? So we've looked at both of these questions, as I said, in some more recent experiments. And just to sort of lay out the first one, where we were looking at how much of the dry period we need to cool animals for, we set this study up very similar to our other studies, where we have animals that are either cooled or heat stressed from the time that they're dried off. Panel A and B just show you the responses during the first part of the dry period in terms of rectal temperature and respiration rate of the animals that are under cooling or heat stress conditions. And what we did was put them all onto these treatments as they dried off, and then monitored them for the next 3.5 weeks. And as you can see, we got exactly what we expected in terms of the rectal temperature being lower in the animals that are cooled versus those that are heat stressed. Typically, we see about 4 to 5/10 of a degree Celsius average reduction in body temperature in the animals that are cooled versus those that are heat stressed. And respiration rate is going to be elevated in those animals that are heat stressed as well. Exactly what we expected during that first half of the dry period. And then halfway through the dry period, we took each of these groups and split them in half and transferred them to the alternative treatment. So for the entire study, we ended up with 4 treatment groups: animals that were cooled for the entire dry period, animals that were heat stressed for the entire dry period, cows that were initially cooled for the first half of the dry period and then heat stressed, and then cows that were heat stressed for the first half of the dry period and then cooled. And all of the temperature and the respiration rates fell in line exactly as we would have expected, given the animals' treatment that they were on during those time periods. So we got an elevation in rectal temperature in the cows that went from cooling to heat stress, and a reduction in those that went from heat stress to cooling. And the same thing for respiration rate. But that was where sort of the expected results, or ones that met our expectations anywhere, ended. When we looked at gestation length, which traditionally we can expect a reduction in gestation length with heat stress during late gestation relative to cooling, and we saw that in our animals that were heat stressed for the entire dry period. But we also saw a reduction in gestation length in both of the switch groups. They weren't any different from the cows that were heat stressed for the entire dry period, yet they were lower than the animals that were cooled for the entire dry period. And that, of course, led to the corresponding decrease in dry period length for the animals that were heat stressed the entire dry period or for any phase of the dry period. So heat stress at any time seems to have reduced gestation length and dry period length relative to cooling. And we think that this is an initial indicator of some issues with placental function. And I'll come back to that as we kind of come into our wrap-up phase of some of these controlled studies, where we think that initially this heat stress is probably acting at the placenta to influence not only the calf's development, as we'll see in a few slides, but also that placenta is producing hormones and other factors that influence mammary development. And that is then affecting how much capacity these cows have for milk production in that next lactation. And in fact, when we look at milk production, we saw, consistent with the effects on gestation length and dry period length, the cows that were cooled for the entire time, those open symbols at the top, made more milk than any of the other groups. So the cows that were heat stressed for the entire time in the open circles made less milk than the cows that were cooled for the entire time. But both of our switch groups also made less milk than the cows that were cooled for the entire time. So our interpretation of that is that any heat stress during the dry period is going to have a negative impact on animals' productivity in that next lactation, and it would be consistent with those alterations in placental function and output of particularly some of the hormones that are produced by the placenta that may influence mammary development. And we've shown previously that there are reductions in mammary cell proliferation in the animals that are heat stressed late in gestation versus those animals that are cooled. So from a management perspective, we need to cool animals for the entire dry period in order to realize some of the benefits. So now what about that second question where we wanted to know about heifers coming into their first lactation? So these animals were taken off of pasture in the summer here in Florida and moved into our freestall facility. So they went from an open pasture with limited shade to a shaded freestall barn. And we found that the animals that moved in that were exposed to active cooling through fans and soakers had a lower respiration rate relative to the heifers that were in the barn but only exposed to shade. And then those animals that were exposed to cooling had lower rectal temperatures for that entire 60-day period before they were due to calve in relative to the heifers that continued to be exposed to heat stress conditions despite the fact that they were now in the barn. And then when we looked at milk production in their first lactation, similar to the mature cows, the animals that experienced heat stress late in gestation made less milk versus their herd mates that were coming into their first lactation but were cooled during that late gestation phase. So this is a very consistent biological response. Animals that experience heat stress, whether they're coming into their first lactation or their fourth lactation, are going to have lower productivity in that next lactation. So what we like to think is that cows that experience heat stress in late gestation are being programmed for that next lactation to exhibit a lower productivity phenotype. Now, we don't think that has long-lasting implications for subsequent lactations, but at least for that lactation, they are going to be programmed for lower productivity, and it appears that that lasts for the entire lactation. So now let's transition over and talk about what's happening with those calves. We'll look at some early life factors as they move into the production string, and then finally what those animals are doing as they mature and are in the lactation cycle. So just to provide a little bit of background, we looked first at birth weight in calves in our studies that were born to dams that were heat stressed or dams that were cooled. And we see that those calves are going to be born at a lighter body weight relative to their herd mates that are born to a cooled dam. This isn't anything new. This had been shown previously by other researchers, but we then went on to look at some later life effects of this initial reduction in body weight. In addition, we've looked at immune status early in life. And here we have data from one of our first studies, immunoglobulin concentrations in these animals at day 1, all the way through the first month of life. We see that the calves that are born to a heat stress dam have lower immunoglobulin concentrations represented by the open circles relative to the calves that were born to cooled dams. And that persists through that first month of life, which is, of course, the time when their own immune system is really becoming more developed and able to protect them. So when we look at Ig concentrations in the colostrum that these animals received, there wasn't any difference between the cows that were exposed to heat stress versus those that were cooled in terms of Ig concentration. Now, there was a volume difference, and we've seen that repeatedly, but all these calves received the same volume, about 4 liters of colostrum, very early on after birth. And all the animals were tubed, so we know that they got the colostrum that we intended them to get. So these lower concentrations then indicate that the apparent efficiency of immunoglobulin absorption is reduced in those calves that are born to a heat stress dam relative to the animals that are born to a cooled dam. So one limitation of this study, though, was that even though they got colostrum that didn't differ in immunoglobulin concentration, there may be other factors in the colostrum that would influence their capacity for uptake. And all of these animals got colostrum from their own dam. So if a cooled dam somehow expressed some other factor that would influence Ig uptake, we wouldn't have been able to tease that out from this study. So to look at that more closely, we set up a second study with a couple of experiments. In the first one, we had calves that were born to heat stress cows and calves that were born to cooled cows. And instead of getting colostrum from their own dams, we had made a pool of high quality colostrum from another source. And the calves, whether they were born to a heat stress dam or a cooled dam, all got colostrum from that source. We then took the colostrum that these cows produced that were heat stressed and made a pool, and colostrum that these cows that were cooled made and made a second pool. And then we fed that to calves that were born under cooler or thermoneutral conditions. So what we're trying to do here is look for an effect on the calf itself in the first experiment, or an effect of the colostrum in the second experiment. And in terms of results, when we look at the growth impacts of these animals in the first experiment, exactly what we had seen previously. Calves that were born to a heat stress dam, lower birth weight, lower weaning weight as well. And here's where we started to get some additional information that hadn't been looked at previously. These growth effects appear to persist for a longer time than just around birth. We also have an indication that there may be some differences in the composition of gain, because the calves that were born to cooled dams were actually taller early in life and all the way through weaning relative to those animals that were born to heat stress dams. So along with some other data that we have, it suggests that there may be differences not only in absolute body weight, but also the composition of that body weight gain in those animals as well. And then we looked at apparent deficiency of immunoglobulin absorption. And again, similar to our earlier studies, the calves that were born to a heat stress dam had lower Ig uptake relative to the calves that were born to a cooled dam. So that suggests that despite the fact that they received immunoglobulin from colostrum, all from the same source, there's something influencing the capacity of these calves that experience in utero heat stress to take up that colostrum that they're fed. And so that may mean that there's a bigger problem with overcoming this in those animals after they're born, and we may not be able to manage our way out of this after those calves are born. But we really had to do that second experiment in order to confirm that we weren't seeing additional effects of the colostrum as well. So just to remind you, in this case, we were testing the effects on colostrum. So it was the pools, either from cows that experienced heat stress late in gestation or cows that were cooled. All the calves were born under cooled conditions, so we didn't expect there to be any differences in birth weight. There weren't. No differences in weaning weight or pre-weaning gain. No effect overall on animals' indications of growth, given that they got colostrum from different sources. And then, in fact, when we looked at apparent efficiency of absorption in these two groups of animals, there was no effect. So the apparent efficiency of immunoglobulin absorption was identical, regardless of the source of that colostrum, whether it was from cows that had been heat stressed during late gestation or cows that were cooled. So that really sort of suggests that this is an effect on the calf itself, and it may be much more difficult to overcome this, say by giving additional colostrum, giving it sooner after that animal's born. We can't really overcome this by post-parturient management. And we've since gone on to look at some of the mechanisms for this. The first study, we were really just looking at the impacts on gut closure. The idea being that that initial layer of enterocytes that calves are born with, somewhat more leaky than what they will eventually have. And those cells turn over very rapidly during the first day of life. And the idea is that as they turn over, tighter junctions are formed, which limit the capacity for immunoglobulin uptake. And what we found using apoptosis, which is just an indicator of cell death or cell turnover, it's actually accelerated in those calves that are born to heat-stressed dams versus those that are born to cooled dams. So their gut closure is already well underway, even at the time of birth, if the animal has experienced heat stress in utero versus those that are cooled. And so we really can't, again, overcome this once the animal is born. We need to address it before birth in order to improve their capacity for passive transfer. So we were interested in how some of these impacts on growth and early life immune status might affect the animal's ability to persist within the herd and their productivity later on. Didn't generate enough calves from any one experiment to really look at some of these long-term impacts. So what we did was combine data from calves born on multiple studies. Now, all the calves from our studies here at the University of Florida would have been maintained here in our calf development program and would have then moved into their first and greater lactation here in our herd as well. So a very consistent management of those animals across this 5-year span, even though there obviously were differences in the number of animals that were born each year. So when we looked at the sort of overall patterns, they didn't change from year to year, but what combining the data set allowed us to do was to get enough animals to really make some inferences on effects on growth and survival in particular. So we ended up with over 40 heifers across this span that we could follow through their first and now in greater lactations. We looked at some early life events in the bulls as well, but primarily we were interested in these 40+ heifers in our cooled group or in our heat stress group. and tracking them initially, at least through their first lactation, and we've since gone on to look at subsequent lactations as well. So combining the data set, these are the body weights in the heifers that were born either to heat stress dams in the open symbols or cooled dams in the solid bars. And we see that in the overall data set, the lower birth weight persists, the lower weaning weight in the animals that were heat stressed in utero persists, and in fact, out to a year of age, around the time of puberty, you still see that those calves that a year earlier were born to a heat stress dam have a lower body weight when compared with the animals that were born to a cooled dam. So long-term impacts on growth, or at least body weight accumulation in these animals if they experience heat stress in utero versus the animals that were cooled. In terms of survival then, if we focus in here on the heifers that left the herd before puberty, mostly this was due to sickness. We see that the heifers that were born to heat stress dams had a much higher number leaving the herd before puberty relative to the group that was born to a cooled dam. And that then translated to fewer of those heifers born to the heat stress dams making it through their first lactation relative to the ones that were born to cooled dams. So consistent with some of those early life challenges from an immune status perspective, we see that those calves didn't make it even through puberty in certain cases and didn't make it through into their first lactation. That is, if they were heat stressed in utero versus the animals that were cooled in utero. So long-term impacts on herd survival if those animals experience heat stress in late gestation. In terms of reproductive performance, when we did this initial look at the animals that we had, very low numbers obviously, but all of the indications were that there was a challenge from a reproductive performance standpoint if the animals were heat stressed in utero versus those animals that were cooled. They took more services to get pregnant. Their age at pregnancy was a little bit older, and those animals had poorer reproductive performance in general, even though the number of animals is very low here. So in terms of what is associated with this or what's causing this, we've since done a slaughter study where we looked at early life developmental effects on multiple tissues, but in particular, we've looked at the reproductive performance of these animals in reproductive tissues. And one of the first things that was observed is that the animals that are born to a heat stress dam early in life have lower anti-Müllerian hormone concentrations relative to the heifers that were born to cooled animals. And this is important because there are associations of anti-Müllerian AMH, anti-Müllerian hormone concentration, and reproductive capacity, in particular the follicular reserve in those animals. And the idea is that lower AMH, lower follicular reserve, poorer potential reproductive performance in the animals that were heat stressed versus the calves that were born to a cooled dam. In fact, looking at not just hormone concentrations, but in some of these calves that were slaughtered, we see that there is a profound difference in terms of reproductive organ development in these animals, particularly in terms of the ovarian development. So ovarian size, not really different at the time the animals were born, but by puberty, by weaning, there were already dramatic reductions in ovarian size in the calves that were born to a heat stress dam relative to those that were born to a cooled dam. And that's illustrated in the two representative pictures on the right side of the screen, where you see much greater ovarian development in the animals born to the cooled cows versus those born to a heat-stressed animal. So all of that would be then consistent with poorer reproductive outcomes long-term in the calves that experienced heat stress late in gestation versus their cooled herd mates. And when we look at productive performance in those animals, again, going back to that first data set that we had, we saw that there were dramatic reductions in first lactation yields in the animals that had 2 years earlier been heat stressed in utero versus their herd mates that were cooled in utero. So there wasn't any difference in how they were managed after birth. They were all managed at our University of Florida dairy facility. They were all fed the same diets, raised. They were born at the same time of year. And yet, 2 years later, those animals that had been heat stressed in utero produced less milk in that first lactation versus the animals that had been cooled in utero. There's no difference in how they were managed during lactation. They were all calving at about the same time. They were all really within the same pen. The only potential explanation for this could be that there were differences in, or one of the potential explanations could be that there were differences in genetic potential. We looked at that, there were not. The other thought that we had was, we know that these animals that are heat stressed in utero are lighter at birth, they're lighter at weaning, they're lighter at the first year of life. And as there are associations between body weight at calving and productivity in that first lactation, the idea would be that perhaps these animals that were heat stressed in utero are continuing to sort of accumulate body weight, that they're seeing some compensatory gain even into that first lactation. And once they get through that compensatory period in the second lactation, third lactation, they'll recover and produce as much milk as their herd mates later on. But when we looked at body weight in those animals, the compensatory gain had already occurred. So these are the body weights of those first calf heifers from the time of parturition through that first lactation. And we see that there was no difference in body weight at the time of parturition, no difference anywhere through that first lactation. They had already accumulated additional body weight between year 1 and year 2 of life. So they had already caught up from a body weight perspective. And any differences in growth then couldn't explain those differences in milk yield in that first lactation, and suggested pretty strongly that we were going to see differences in output throughout the next lactations that these animals had as well. And in fact, as we accumulated more and more records from animals that went through our controlled studies, that's exactly what we see. In terms of the first lactation drag, it's about 2.2 kilos, so about 5 pounds a day less production in the animals that are born to a heat stress dam versus those that are born to a cooled dam. Similar, perhaps a little bit more in that second lactation, and it really starts to spread out as we get into the third lactation. Those animals that were born to a heat stress dam 5 years earlier make less milk than the animals that were born to a cooled dam, just because of that relatively brief insult late in fetal development, late in gestation. We can have profound long-term effects on the productivity of those animals. And in fact, it's not just productivity. We also see that those animals do not persist in the herd nearly as long. So what's represented in panel A is the survival of calves that were born either to cooled dams in the blue line or heat stress dams in the orange line. And we see that for the daughters of those animals that were heat stressed or cooled in late gestation, the ones that were born to a heat stress dam, about a year less time in the herd relative to those born to cooled dams. And so a long-term negative impact on persistence within the herd just from experiencing heat stress during the very final phases of fetal development. And what perhaps is more of a problem is they appear to pass that on to their offspring. So we see that the granddaughters, so the daughters of these animals that experienced in utero heat stress or cooling, those animals that are born to those that experience in utero heat stress, even if they're not heat stressed in utero, lower survival versus the animals that were born to cooled dams. So long-term transgenerational evidence of negative impacts of in utero heat stress, particularly on herd survival. So why might this be? What's happening in those animals in utero that is decreasing their long-term productivity? Well, again, going back to a recent slaughter study where we sacrificed calves at birth and also at weaning from dams that were either heat stressed or cooled during late gestation, we see that even at birth, there is a reduction in mammary development in the animals that were born to a heat stressed dam versus those born to a cooled dam. And in fact, this becomes even more apparent when we do the analysis of mammary development at the time of weaning. Much greater proliferation and tissue capacity for mammary development in the animals born to cooled dams versus those born to heat stressed dams. And in fact, when you look at it at the cellular level, the proliferation, excuse me, is greater in calves born to a cooled dam at birth versus those born to a heat stress dam. And that persists as the animals get out to weaning as well. And the idea would be that they are going to have less capacity long-term for mammary productivity because they are expressing a lower productivity phenotype through this reduction in mammary tissue development. So all consistent with those animals having long-term programmed lower productivity phenotypes if they experience heat stress in utero versus animals that are cooled in utero. So in terms of the impacts that we see in those calves, when mom is heat stressed late in gestation, that calf that results from that is going to have a lower birth weight, lower immune status, lower weaning weight and survival rate early in life, and she has lower milk yield in her first through third lactations. So along with the potential issues that we see in terms of reproductive performance and in other areas that suggest that that animal is going to have lower survival long term, as our initial analysis indicates. And so that may impact then the longevity. So the idea that we wanted to look at was whether animals had a season of birth impact on longevity. So to look at that, we collected data from some large herds that we work with in Florida and also in California, and just asked the very simple question, is there an impact on longevity, or at least the age when those animals, or the lactation number that those animals are in, that extends out if animals are born in a cooler season versus animals being born in a hotter season. So what we looked at was cows that were in their 5th, 6th, 7th, or 8th lactation. And you can see that there's obviously declining numbers as we get further and further out and longer lived animals. But we, in the Florida herd, found that there was almost 3/4 of the animals in these later lactations in the herd were born during the cooler season of the year, December, January, February, March, relative to animals born in the hotter season of the year. So significantly more animals persisted and had a longer life, consistent with our controlled studies, if those animals were born under cooler conditions relative to animals that were born under hotter conditions. In terms of the California herds, similar pattern, not quite as dramatic, but still significant, that the animals that were in these later lactations were going to be more likely to be born under cool conditions relative to the animals that were born under hot conditions. So suggesting that there is a season of birth effect on persistency within the herd and how long those animals are going to last. And that obviously becomes a factor when we start thinking about replacement animals, and with the fact that we're now seeing a lot of use of sex semen and on the top end of the animal herd, and beef breeding at the lower end of the herd. We may want to think about when those animals are actually calving in, that are producing the next group of heifers entering our production cycle. In terms of the reason why animals left the herd, in terms of the Florida animals, more of them left the herd because they were sold. So they were able to market those animals versus animals dying. There was a tendency for more of the animals to die if they were born under hot season, similar to significantly higher number of those animals being sold, particularly in that first lactation. But overall consistent with the fact that these animals were leaving the herd sooner if they were born in a hot season versus those born in a cool season. In terms of the reason for them being sold, all of the sorts of things you'd expect, primarily breeding issues, feet and legs, all increased in the animals born during the hot season versus the animals born during the cool season. In terms of mastitis, again, more of them being sold if they were born in the hot season due to mastitis issues versus the animals born in the cool season. In terms of other reasons, no difference in terms of respiratory or digestive issues in the animals in terms of season of birth. So all of the sort of top productivity, reproductive, and physical limitations that we see animals being sold for in general in a herd. In terms of California, more of an impact on cows dying within the herd versus those animals being sold. So we lost more potential animals just due to death rather than being able to market those animals in the California data set if they were born in the hot season versus animals born in the cool season, particularly as we move out into second and greater lactations. So looking at the impacts of birth in a hot season, they're really consistent with our controlled studies where we see a greater number of animals persisting within the herd if they're born under cooled conditions versus those born under hot conditions. And it really, I think, makes the case for making sure that we do as much as we can to limit exposure to heat stress even during the dry period, during late gestation, in order to realize some of the benefits of cooling, not only in the cow in the next lactation, but also in these calves. Because we think that longevity is going to be programmed by in utero and early life events. So those animals that are going into that sixth or seventh lactation, that's because they were born at the right time of year, and there's other management factors that would influence their persistence in the herd, but one of the big ones may be some early life impacts, particularly heat stress in utero. And we want to consider this when we're selecting heifers for the future production herd and when those animals are born, and how we manage this is going to be important to our overall productivity. So just to sum up, in terms of the impacts of late gestation heat stress in the cow, we're going to see dramatic effects programming her to have a lower productive phenotype for that next lactation, primarily due to limitations on mammary development in that cow, but we do also see some impacts on immune function in that cow as she goes into that next lactation. none of them are positively associated with heat stress. In terms of the developing fetus, those impacts are longer term and are going to persist for the life of that animal as long as much as we can tell from data that we have at this point, and studies are ongoing, and all signs are that those animals have a lower productivity phenotype for their entire life, and that they pass that on to their offspring as well. I think a lot of this insult starts at the level of placental function. And so we're actively investigating impacts on placental function and looking for potential ways to overcome some of these effects of heat stress in utero. But at least right now, the only way to really overcome it is to make sure that our cows late in gestation have good cooling, as good a cooling system as we would have in our lactating cows. So with that, thank you for your attention. Just want to highlight some of the students that have worked on this and other collaborators. Dahl did a lot of the early work looking at milk production, productive function. Burroughs Ahmed did some of the early work on calf development. Ana Montero actually did that first analysis where we saw the impacts of in utero heat stress on development of those cows. And Isabella Toledo, who did graduate work here and is now a colleague working on some of those analyses of longevity. Amanda Laporta was here at the University of Florida, now at the University of Wisconsin, following up on some of these studies. Was really the driving force behind a lot of the work that I showed you with fetal development. And in fact, Bethany Dedosen did some of the work with mammary development, and Brittany Davidson would have been responsible for the work on reproductive development in those animals. So thank them and other collaborators and support that we've had for this work from NSF, USDA, and also industry partners. So with that, happy to take any questions that you might have and turn it back over to you, Abby.
Thank you so much, Dr. Dahl, for that presentation. You and your team really have been leaders in this area of heat stress for quite a few years now. So really appreciate you taking the time to share some of the research that you've done and the insights you've gleaned from the work that's been conducted at the University of Florida and elsewhere. So thank you very much. If you are interested in watching this presentation again or sharing it with somebody, a friend or a colleague, it will be posted on our website later this week. You can find this webinar and all of our past webinars at our archives, which are available on our HORDS website at hords.com, and there's a webinar tab where you will find them. We hope that you'll make plans to attend one of our future webinars. We have two coming up. The webinar in May, if you want to click ahead one slide, Dr. Dahl, will take place on May 13th, and the focus of that presentation will be managing and feeding cows in a robotic milking system, presented by Jim Sulfur from the University of Minnesota and sponsored by Galaxy. And then our June Dairy Month webinar will be a focus on feed additives, and our presenter will be Mike Hutchins from the University of Illinois. That webinar will be sponsored by Protecta. So if those topics interest you and the dates work, we really hope that you'll make plans to join us for one or both of those presentations. As always, our webinars take place on the second Monday of the month at noon Central Time. Now, we did have some questions that came in. If you'll move ahead just one slide, I'll start going through these. We really appreciate our audience members being active listeners and then asking some really good questions, so I'll just dig in. First question, what do you consider to be the most impactful cooling solutions? You know, if a farm can't do everything, what do you think has the most impact and provides the greatest benefits if you're trying to implement some sort of cow cooling?
Well, part of that is going to depend on where you're located. I mean, here in Florida, obviously, with our high heat and humidity and the fact that it goes pretty much year round, we really only can use evaporative cooling. So we have to get cows soaking wet to the skin and then put them under air, moving air that's going to pull some of that water off and pull the heat off with it. I would say that in a lot of areas in the Northeast and the upper Midwest, your summers will be hot and they will be humid. Perhaps not quite as humid as we are here, but you can't really cool the air. You have to cool the cow. And so in those areas, the most effective way to get cows cooled is typically getting them wet and then moving air over them to take advantage of evaporative processes. In some areas where we have a more arid environment, particularly in the Southwest, other areas of the world where we might have drier conditions, we may be able to use some of the systems that are available to actually kind of cool the microenvironment around those cows and cool the air. But that's going to be kind of limited in terms of the geography where we can use those, particularly in the US. I think we're really going to have to get animals cooled off effectively with water and with air movement. Now, the first thing we want to make sure is that they have shade, that they have access to good water. Those kind of are the baseline no matter where we have animals. But then in order to get into active cooling, we're going to have to get them wet and move air over them to remove some of that heat.
Tying into that, someone's asking, why do you think some cows and lactating and dry cows prefer to lay in the sunlight when shade and fans are available to them?
Yeah, well, I think that just goes to the fact that some cows are better able to resist heat stress and versus other animals. It's like people, right? We have different tolerances for heat and cold. That's one of the areas of research, colleagues here and elsewhere, trying to select animals that are more resistant to heat stress. Particularly animals that we're going to be selecting for production. One thing that we have observed is that there are differences in animals' tolerance for heat if they've been heat stressed in utero versus the animals that are cooled. We did a study where we looked at taking calves that had been born to heat stressed or cooled dams at maturity. So they were in their first lactation, and we just gave them an acute heat stress. And those animals that had been born to the heat stressed dams actually didn't have as much of an elevation in temperature as the animals that were born to cooled dams. Of course, the trade-off is that those animals are less productive. So folks have gone on, particularly Amanda Laporta's group, to look at differences in sweat gland and other sort of skin differences that might be related to the ability to get rid of heat. And we see those persisting in animals, even in subsequent generations. So it's an adaptive response that different animals have that are better able to get rid of heat versus others. What we want to do, though, is look for the genetic component of that, where we can select for animals that are not just more resistant to heat because they're lower productivity, but they are higher productivity and still more resistant to heat.
Great, thank you. How is heat stress defined for the purposes of these studies?
Well, we look at rectal temperature, we look at respiration rate as sort of cow-based indicators of heat stress. What I would recommend for everyone, rather than looking at the daily temperature, the THI, look at a cow-based indicator, and probably the easiest one to track is respiration rate. We did an analysis of 4 or 5 data sets from different studies, trying to get a handle on the respiration rate that was associated with an increase in rectal temperature that was indicating heat stress, because rectal temperature is a little more difficult to track, obviously, particularly in the production environment. So respiration rate, it's an observational variable. So we can just watch cows and take some sentinel cows and look at the respiration rate through flank movements. If we see respiration rates going above 60, that's an indicator that cows are beginning to be heat stressed. And as we get higher and higher on the average respiration rate, that means the animals are more and more heat stressed. So very simple solution, not worrying so much about the absolute temperature or what the humidity might be, but just looking at the cows in whatever facility we have, because we obviously have differences in facilities design as well that may influence this. We can simply take respiration rates in a group of cows to get an idea of the access to heat stress or the exposure to heat stress that those animals might have.
All right. Interesting question here. How does heat stress affect embryos and embryo transfer? Like if an embryo is produced by an animal that was in a cooler climate and then put into an animal that was in a hotter climate, or what is the difference between embryos that are producing cows that are heat stressed or not heat stressed? Do you know of any work in that area?
Yeah, I don't know specifically animals that were, the embryos were produced in cooled animals and then put into heat stressed animals, except for work that was done here in Florida, making a comparison between embryo transfer and AI during the hot phase of the summer. And they found that the in vitro produced embryos, they did better than the animals that were just bred to AI. So the idea being that those embryos were more resistant to early embryo loss if they were from embryo transfer process rather than the normal AI process. There are data out there that suggest that heat stress exposure, even at the time of implantation, is going to result in a lower productivity animal long term. Now, we don't see very much of that because our animals are typically cooled during lactation, so during early embryonic life, but it is consistent that those animals may have, that there may be even earlier effects on the embryo earlier in development versus the later development that we've looked at.
All right. Have you noticed any breed differences in terms of dealing with heat stress?
Yeah, we have done all of our work in Holstein animals. That's the predominant breed that we would have here. When I've looked at other heat stress responses, certainly there are some indications that some of the other breeds, Jerseys and Swiss, may be a little bit more resistant or tolerant to heat, but they're still affected by heat stress, right? That's sort of more resistant to a degree, but profound heat stress is going to affect cows regardless of whether they're Holsteins or Jerseys or what have you. The caveat to that, of course, is some of our Indicus breeds. And so when we look at areas of the world that may use crosses, Brazil, for example, the Gerolando, those animals are more heat tolerant because of that Indicus breeding, as well as the Bos Taurus genetics that those animals have. But again, they're typically going to be at a lower productivity as well. So I think that that sort of productivity relationship is going to be, even within a breed, one of the factors that indicates how tolerant animals are to heat stress.
Have you done any work with the slick hair gene in your trials?
We have not. Obviously, Pete Hansen, my colleague, who's leading those efforts currently, have worked with him on some of those studies. We do see improvements in animals' ability to tolerate heat stress if they are of slick background, but we have not specifically, we haven't had enough animals, to be honest with you, to really do a study where we put animals on heat stress treatment during late gestation. With slick genetics versus those without. The idea would be that those animals may be more heat tolerant. Again, I'm not sure that we're going to see a complete reversal in those animals, but the more heat tolerant the animals are, the idea would be that they're going to have less of an impact. But you'd need a large number of animals to really tease some of those differences out, and we just haven't had that capacity yet.
Is there any way to combat the epigenetic effects that occur in future generations from a heat stress dam? So maybe 3 or 4 generations out, can producers do anything to turn that around?
Well, that's what we're looking at in terms of manipulation of placental function and some other factors. We're not far enough down the road to tell you anything yet in terms of whether we can reverse some of those effects, but the idea being that we may be able to, with certain factors, reverse some of those impacts. There are data out there that would suggest that there are ways, particularly from a nutritional standpoint, perhaps to overcome some of those negative impacts, but we haven't looked at that specifically in dairy animals yet. But we're working on it.
Great. Because of the profound effects of heat stress during pregnancy, do researchers in hot climates like yours have to take that into account when doing research projects on animals, at different stages of their life?
Well, again, what we look at in terms of balancing out our groups is that we're going to look at genetic factors and other things to make sure that we're not stacking the deck in favor or to the disadvantage of one treatment or another. All of our animals that we use in our studies are just, sort of randomly from our herds. They're going to have been born at different times, but we do take into account genetic influences on those animals, and eventually we'll probably take epigenetic marker influence into account when we make assignments to different treatments as well.
This question is asking about small calf syndrome. So if a calf is less than half the normal birth weight, and they're wondering if there's a specific temperature and heat threshold where this is a higher risk, especially for pastured dairy cows. Comments on that?
Yeah, I don't know that there's a specific threshold. The way that I think about the impacts of heat stress are that it's along a spectrum. And so I tend not to think of a specific amount of heat stress exposure or a level of heat stress exposure. Any heat stress exposure is going to have some negative implications. Whether we're able to really tease those out is going to be a function of how much heat stress exposure the animal had. But I don't think it's we can get away with sort of a lower amount of heat stress to a certain point. I think there's going to be a negative impact no matter what the level of heat stress is, but it just becomes more apparent, more significant as that heat stress gets worse and worse.
All right, thank you so much. That will wrap up our questions for this program. Once again, I'd like to thank Dr. Geoffrey Dahl for the information shared on the impacts of heat stress on dairy cattle. I think this is really helpful for all of us, especially as we head into the summer season in our part of the world. I'd also like to thank all our listeners. I really appreciate all the great questions that came in and that you take time to be with us and be part of our audience during these monthly webinars. I hope that you found some useful information you can use on your farm or on your clients' dairies. And we hope that you'll join us for a future webinar. Until next time, goodbye from our team here at Hordes Dairymen.